The method of integrating factors is a powerful tool for solving differential equations that are first order and linear. Those sorts of equations can be written in the form dy dt plus g of t times y equals r of t. So first order, meaning the highest derivative is the first derivative, and the differential equation is linear. So nowhere are we multiplying y times y prime or taking the square root of y or anything like that. Now, in the next few minutes, I'm going to be writing down a lot of expressions, and I'm going to be a little bit sloppy, I'm afraid, at times. Keep in mind that this y is a dependent variable, so this really means y of t, which is really what I should be writing, but I'm going to be a little bit sloppy. So what would be an example of a first-order linear differential equation? Well, dy dt minus y equals e to the t would be an example. In this case, r of t is e to the t, g of t is negative 1. As another example, dy dt equals t plus y over t. Now, it's not obvious that this is linear, but if we subtract from each side the term y over t and do just a little bit of algebra, we see that we get dy dt minus 1 over t times y is t. So in this case, r of t is t, and g of t would be minus 1 over t. dy dt equals 2 minus y. This is actually a first order linear autonomous differential equation. If we rearrange this by adding y to each side, we see that r of t is 2, g of t would be just 1 in this case. Something like dy dt equals y times 1 minus y. This is logistic. This is not linear, because if we were to expand this, we'd have y times y, which is y squared. So this method would not apply for such a differential equation. So here's the standard form of a linear first-order differential equation. And again, this y is really y of t. I'm going to denote this with an asterisk. And to solve this, we're going to introduce a new type of function known as an integrating factor. And this is the Greek letter mu. And the integrating factor is what you get when you take g of t, you integrate it, anti-differentiate it, and then exponentiate it. So you take e to the antiderivative of g of t. Now, we'll calculate some integrating factors in a couple minutes, but the integrating factor has the nice property. Let's say we take the derivative of this. By the chain rule, it would be e to the integral of g of t. We'd have all of this left alone, and then we'd multiply that by the derivative of what's up here, the derivative of the integral of g of t dt. Well, if you take the derivative of the antiderivative of g of t, you simply get g of t. So mu prime is e to the integral of g of t dt times g of t. But this quantity is really just the integrating factor mu itself. So the integrating factor satisfies this condition. Mu prime is equal to mu times g. Again, everything here is a function of t. So what I claim is that a solution to this differential equation is given by 1 over mu of t, this is 1 over the integrating factor, times the antiderivative of the product of r and mu, and that's a dt. So I claim that this is a solution. Now, the reason that we can divide by mu is because mu is an exponential, so it's never going to be 0. So we don't get in any trouble dividing by mu. Now, how do we know that this is a solution? I just wrote this down. How do we know it's a solution? Well, we can actually check. So here's what I claim is a solution, 1 over mu times the integral of r of t mu dt, and I claim that that satisfies this differential equation. We're going to check that. And again, the integrating factor satisfies mu prime equals mu times g. Okay. So let's cross-multiply this equation, multiply each side by mu of t. So we have mu of t, y of t equals the integral of r of t mu of t dt. Now we're going to take the derivative of each side. The left-hand side requires me to use the product rule. So I'll have mu prime times y plus mu times y prime. And again, everything here is a function of t. And if I take the derivative of the integral of r of t mu of t, I just get r of t mu of t. The derivative and the integral cancel. Now, we know that mu prime is mu times g. So I'm going to replace mu prime with mu times g. And now we have plus mu y prime equals r of t mu of t. Now, mu of t is non-zero. So I can divide by it, and I can rearrange the order here, just switch the order of addition. I can divide by mu, and I get y prime plus g times y equals r of t. That means we've shown that this function satisfies our differential equation, so it has to be a solution. Let's actually look at a couple examples. Suppose we have the differential equation dy dt minus y equals e to the t with the initial condition that y of 0 is 1. In this case, r of t is e to the t and g of t is negative 1. So our first step is to calculate the integrating factor. We take g of t, we integrate it, and then we exponentiate the result. Well, the antiderivative of minus 1 is just negative t, so mu would be e to the negative t. Our solution then is 1 over mu, and then we take r of t, which is e to the t, and multiply it by mu of t, which is e to the negative t. Well, if you take e to the t and multiply it times e to the negative t, you get just 1. Here's 1 over mu, 1 over e to the negative t, which is just e to the t, times the integral of dt. Now, here's where you need to be a little bit careful, because you're going to multiply this e to the t by everything that's inside, which is why I use brackets. When we integrate right here, that's where a constant of integration is going to arise. So we're going to have e to the t, and the integral dt is just t plus a constant. So that constant goes within the brackets here. So if we expand, we get t e to the t plus c e to the t. So this is our general solution. Now we know that y of 0 is 1. So here's y of t, the general solution. If we substitute 0 in for t, we would get 0 here, we would get c here, and we want that to equal 1. So that says that c has to be 1. And our final solution is y equals t e to the t plus 1 e to the t. Now, how do I know that this is correct? I could actually check this by taking that y and showing that it satisfies this differential equation, and that would be a good thing for you to do on your own. Here is another example. dy dt plus y over t is equal to e to the t. And the initial condition is going to be that y of 1 is t. Notice how this is undefined at t equals 0, so I can't use 0 there. In this case, g of t is 1 over t, and r of t is e to the t. So to compute our integrating factor, we have to integrate this and then exponentiate the result. So it's e to the integral of 1 over t dt. Now, the integral of 1 over t dt, strictly speaking, is the natural log of the absolute value of t, but we can get away in this case with using just the natural log of t. So we have e to the natural log of t, and that simplifies using properties of the exponential to be equal just t. So our integrating factor is just t. Our solution to the differential equation then is 1 over mu times the integral of r of t times mu of t. Mu is t, r of t is e to the t, so what we're left with is 1 over t times the integral of e to the t times t dt. And again, I'm going to put everything in brackets here because there's going to be a constant of integration. Now this integral is tailor-made for integration by parts because it's of the form t times an exponential. So we're going to let u equal t, u prime is 1, v prime is e to the t, so v is e to the t. So this is an integration by parts problem. U times v is t e to the t, and then we have to subtract the integral of v times u prime, which is minus the integral of e to the t dt. Now we still have that 1 over t out in front. So we have 1 over t, t e to the t, and then we subtract the integral of e to the t, which is e to the t. And now we have this constant of integration. And again, that's inside the brackets. So if we expand, 1 over t times t e to the t is e to the t, and then we have minus e to the t over t plus c times 1 over t, or c over t. Let's substitute our initial value in. We know that y of 1 is 2. If we substitute 1 in for t, this becomes just c. This would be e to the first over 1. This would be the same thing, so these would cancel. So when t is 1, we'd have a c on the right side, and we know that we want that to equal 2. So c would have to be 2. So that says our solution would be e to the t minus e to the t over t plus 2 over t. And again, we can actually check that solution by substituting it in to the differential equation.